Good morning. I'm John Ortiz. I'm here to talk about advanced steganography, advanced JPEG steganography, and detection. Okay. All right, so one of these two images has about 69,000 bytes hidden in it out of a file size of about 330,000 bytes, which is about 20% of the file. So we can take a closer look. I'm going to dim the lights a little bit for this one. So this is the picture on the left. There's a picture on the right. Left, right. Looking at it closely, especially like if you look above the eye, you might be able to see slight differences. But there's no way you can tell that one of them has hidden data and the other one does not. And that's the hidden data. Just an image. You can actually hide anything inside of a JPEG, whatever you want to hide. So here's what we'll talk about today. We'll overview the JPEG algorithm, then how to exploit it for hiding. I think I've got about 10 different techniques to talk about. And then how to detect exploited JPEGs. And then if we have time, we'll do a demonstration. I've got about 150 slides, so we'll have to go really fast. I'm kidding. That makes 85 not sound so bad. All right. So just a little bit about me. I'm an engineer, part-time professor, and part-time comedian. I was always an engineer from birth. You know, I counted powers of 2 when I was a kid instead of sheep. I know some of you all have done that too. I published my first game when I was 2 to the 4th, and then a couple others throughout college. You haven't heard of them. It's not like Pac-Man or anything. Graduated from school, joined the Air Force, got a master's degree, worked for a bunch of different companies. They keep getting sold. Currently I'm working for Harris IT Services. And I do reverse engineering and malware analysis. So steganography is kind of a hobby of mine. And you won't see any slides about me being a comedian because I'm not that funny. See what I mean? All right, the JPEG algorithm. Super easy. JPEG was developed because there was a big need for data compression, and there still is. JPEG is probably the most ubiquitous file format on the internet. And here's the algorithm. Doesn't it look easy? So we have a color plane conversion. We convert from unsigned to signed. We do this thing called the discrete cosine transform. We quantize it, run length encode it, and entropy code it. So basically we apply some lossy compression and then we apply some lossless compression. So the color plane conversion goes from RGB, which is the normal red, green, blue, to YCRCB. The reason it does that is because we can compress the chrominance components more than the luminance. The human eye is less sensitive to chrominance, so we can actually compress them more and still have a very good looking image. Then we quantize it. It uses different quantization tables for the luminance and the chrominance. That's how it compresses it more. Here's the formula. We're not going to talk about that. We don't have time, but it's there in the slides for your reference, how to convert from RGB to YCRCB. We do a 2-dimensional discrete cosine transform. I don't remember who wrote this. I'll read it to you. The purpose of this is to modulate the influence of different spectral components on the image. All it means is we separate the low frequencies from the high frequencies. The high frequencies contribute less detail, so we can get rid of them and still have a good image. Here's the formula. In the class I teach, we go through it in great detail. It looks really ugly, doesn't it? But it's not. It's actually not that bad. So real quick here, there we go. Basically, the A sub xy is your pixel value, and then this is a bunch of cosine stuff. And x and y go from 0 to 7 and 0 to 7 because it's an 8 by 8 block, which is the size that JPEG uses to work with. And it just adds it all up and multiplies by these cosines. It can be implemented in software very easily with that. Just a 4 nested for loop. Okay? The basis that you see down there, that's a 4-dimensional array. There actually is a use for a 4-dimensional array, and this is it. You calculate all the cosine stuff once, and then you just use it to multiply by the pixel values instead of recalculating the cosine, because cosine calculation is slow. So it's very fast. So on each 8x8 block, you end up doing 4,096 calculations. So in an image that's, what, 512 by 512, that's 6 times 6, 64, I don't know, 4,096 blocks, each with 4,096 calculations. Seems very slow. So people ask me all the time, well, how long does it take to do all that? Well, when you open a JPEG, it does all that. So that's how long. 3.6 gigahertz is really fast. Then after we do this cosine transform and we quantize it, we divide the 8x8 block by another 8x8 block, the quantization table. We end up with what's called the quantized DCT coefficients. That's where the steganography happens, in the quantized DCT coefficients. So that's why it's important to kind of at least have a rough understanding of how the JPEG works. Now, from there on, after you get the quantized DCT coefficients, the compression is lossless. So whatever you change those coefficients to, the run length encoding and the Huffman coding, that gets saved to disk. Those changes are saved to disk. They're not compressed away anymore because there's no loss in those processes. So here's a mandrel, which is a very common image when you're working with steganography. You'll see this mandrel image all over the place. And the numbers you see on the screen are the actual values from that file. Now, this is a grayscale file, so there's no chrominance component. There's only the luminance component in this one. I expanded the pixels so you could see the colors and see the actual numbers that are there. So here's the actual numbers. Here are the DCT values. After taking this 8x8 block and putting it through that discrete cosine transform, you end up with these values. Okay, and those are the actual values. Then we apply this quantization table, and my hand always shakes. That's why I'm not a surgeon. I don't want to say oops. So we take this value here and divide by that value there to get that value there. I'm just going to have to use this screen. We take this value here, divide by that value to get that value, and so forth. So, in other words, for each element in the DCT array, we divide by the corresponding element in the quantization array. And the result is this one. So notice all the zeros. A lot of those values go away, leaving only a few up here. And then that portion is run length encoded and Huffman encoded. So it's compressed and then compressed again. And that's why JPEG does so well. It adds pattern and then it gets rid of a lot of stuff that you can't see. Well, here's the numbers after quantization, and now we're going to go backwards. Okay, this is if you're opening a JPEG on a disk. So we take that number, multiply it by that number, and we get that number. That one, multiply it by that one, get that one, and so forth. Okay? These are the dequantized values, and then these are the original values. So there's a big difference, right? This is negative 384, this is negative 377. And there's a lot of zeros down here. But that's okay. The picture still looks good. And then when we run this through the reverse DCT algorithm, which is very similar to that other formula I showed you, okay? You run it through the reverse, and you get the new actual pixel values. These are the actual pixel values in the result. They're not exactly the same. 127, 129, 147, 145, but they're close. And so it still looks good. It's different mathematically, but visually to us humans, it looks very close. So there's just a sample calculation for that 512 by 512 image, as I mentioned. So there's 16 million calculations for an image like that, plus the Huffman encoding, the color plane conversion, the run length encoding, and all that. And a 512 by 512 is a pretty small image on the screen. But we have fast computers, so doesn't bother us. All right. You've got to understand the DCT coefficients, so I'll say one more thing about those. You do all the math, you get these values, you quantize them, and then those are the numbers that you can manipulate for hiding. Those are the numbers that we manipulate, and there's a bunch of different ways to manipulate them, and we're going to look at, I think, about 10 of them. The first one is called swap DCT. This one's kind of interesting. It's different than a lot of others. This came directly from a published paper. The author picked some DCT coefficients. I'm going to try the mouse here. That might be better. You see? Can you see? Yeah, we can see that also. So you pick, this is the quantization table, so you pick a couple of coefficients ahead of time, either the 14s or the 24s or the 22s. Pick one of those pairs. And then you do this for each 8x8 block in the image. So you read the image, do all the math, and you get your 8x8 block of DCT coefficients. And then you read your message. And the message can be anything. It doesn't have to be a picture. It can be a PowerPoint slide presentation. It can be an executable file. It can be a zip file. It can be encrypted. It doesn't matter. The message to the hiding algorithm looks just like a stream of bits. Just reads them bit by bit. So you read your message, and you look at the coefficient value. Now remember, what's on the screen here is the quantization table. That's not the coefficient values, that's just the quantization table showing which pairs of coefficients we chose to hide in. And you look at your message, and it's arbitrary which way you go. But we'll say if your message bit is a 0, then coefficient 1 has to be greater than coefficient 2. If your message bit's a 1, then coefficient 2 has to be greater than coefficient 1. So sometimes that's already true. Sometimes when you check the coefficients, the correct ratio is already valid, so you don't change anything. Your message is already there, and you go on to the next block. If your message isn't there, then they swap the DCT coefficients, so they're in different positions, so that now it is true. And you don't have to, that's all you have to change, and then you go on to the next block. So basic algorithm, select a cover block, get the DCT transform, read the message bit, check the ratio. If it's true, don't change anything, move on to the next block. If it's not true, swap the coefficients, move on to the next block. So on extraction, all you have to do is read the file, look at the coefficients, and say if C0 is greater than C1 or C1 is greater than C2, it's a 0, and if C2 is greater than C1, it's a 1. Extract that out and save it. Go to the next block until you save all your bits. I will mention these authors use the unquantized coefficients. I don't know why. It makes it a lot harder to work with. I did implement this algorithm in the Steg JPEG program, which all of you are welcome to have. If you want the program, you can email me or whatever, and I'll be happy to make it available to you. But I did not work with the unquantized coefficients. I worked with the quantized coefficients because it was a lot easier. Well, this has kind of got low capacity. You can only do 1 bit per block. So with the 256 by 256 image, you get what, 1024 blocks, 1024 bits. So that's only 128 bytes. Not very much. You could use all 3 pairs. Well, some other authors came along and decided to improve on that a little bit. And they used a set of coefficients to swap. And they actually had a set of, 8 coefficients and said, well, we're going to pick 3 of these 8 coefficients and then use those ratios to swap. Okay, we get a little bit more robustness out of it and get a little bit, we get the same capacity, 1 bit per block, but it gets harder to extract because the extractor needs to know for each block which coefficients did we pick. In the other method, we just simply use the same coefficients every single time. Okay. In this method, they're picked from a set of coefficients. So I looked at that and I thought, well, why just 2 coefficients or three coefficients or 4? Why not use all of them? See how that works. So I have 31 pairs of coefficients in this particular implementation. Now, I found that you don't want to use the DC coefficient, which is that one, because you change that and it really distorts the image a lot. I also found that using these two really distorts the image a lot. So the program does allow you to use those two, but you'll get a really distorted image, as we'll see. All the rest get to be used, and we'll see the results. I found experimentally that I can use up to about 24 pairs of coefficients, and the image will still look pretty good. So I just show the matching pairs up here that I chose, and the program will go through each block and just go through all the matching pairs. Now, one thing my implementation does is it does not make any changes to the values of the coefficients. So if they're equal, it just skips them. So if they're equal, then it doesn't change them. Other than that, it can use them to swap. And there's a reason for that, and we'll see that when we get to the detection part. So here's an implementation. I used 24 pairs in this particular case. So 6.5% random bytes hidden in this image. About 10 bits per block on average, or almost 11. And so much higher capacity. And I still, it's not as clear on the screen, of course, but even on the monitor, zoomed in, I can't see a difference. So that is implemented on the program. Here's where I use 31 coefficients. Can anyone see a difference on that one? Yeah, you can really see the distortion, right? That's pretty clear on that one, that is distorted. And if you look at it closely, what you find is kind of the block is reversed. Like if it's got the dark on half of it and the light on the other half, it's kind of mirrored on there. So 31 was too much if you care that it gets noticed by a human. Of course, sometimes you may not care if it gets noticed by a human. You know, you're trying to protect your network. Who's the guy that has to sit around and look at all the JPEGs that come across? I did a demo once, and just browsing websites, within a minute, I got thousands of little JPEGs that were downloaded to my computer. So sometimes when you're hiding this stuff, you don't even really care if it's noticeable by a human. Maybe you only care if it's noticeable statistically, okay? But this will look and feel like a JPEG to any program that analyzes it, as far as checking the validity of the file. Well, you can also add cryptography to the mix. So for any one of these techniques, you can just encrypt your message before you actually put it in there, and that'll complicate extraction, because then after you extract it, then you got to decrypt it, right? But doing that's no fun. So I built a little cryptography into the program. It'll do some XOR cryptography and some permutation. Now the permutation is cool because it will then spread the message over the entire image. For instance, if the message is smaller than the capacity on a JPEG, it comes from top to bottom, and so you would see distortion in the top half of the picture and not distortion in the bottom half. So that's a very clear indication of something is going on. So looking at the 24 pairs, I saved each pair in a list as it went through, so as it processed the JPEG, it just saves them out in the list. And then later, when it's all done, it reads the message, permutes the list, and swaps the coefficients as required. So it's spread cryptographically over the entire image. All right, so that's the swap technique and a couple variations. Then there's the least significant bit technique. You've probably heard of least significant bits with respect to bitmaps. Well, we can use the least significant bit of the quantized DCT coefficients, just as the way you can with bitmaps. You get a lot more capacity than 1 bit per block. Basically, you get 1 bit per, non-zero or non-1 coefficient. You cannot use the 1 coefficient to hide a value, because if your message bit is a 0, then the 1 changes to a 0, and now you have a 0 there. And if you use 0 to hide, you're going to end up changing a lot of zeros to 1s, which is going to vastly increase the file size and also be very noticeable. So we don't use 1, we don't use 0, but everything else we can use. We can use -1, because when you change the least significant bit of a -1, try the mouse again, there's a -1 in binary. It changes to a 0, and that's actually a -2. So -1 becomes -2, not 0, when you change the least significant bit. So here's an image I hid using the LSB technique, quality 65. The standard quantization table that I showed you, just for a frame of reference, is a quality of 50. Okay? So that's kind of right in the middle. And then you can make a higher quality by putting lower numbers in there, and you can make a lower quality by putting higher numbers in there. The higher the numbers that you divide by, the more zeros you get in the output. Most JPEG editing programs that I've seen will allow you to adjust the quality, save it as high quality or low quality type thing. So quality 65 is what is used for this. You have a storage capacity of about 50,000 bytes, which is about 15% of the file size. At quality equals 100, we have a storage capacity of 97,000 bytes. So about 40,000 bytes more. It's better looking, but the file size is larger. But who cares? I mean, how many of you look at the file size of your JPEGs? I mean, maybe, you take pictures with your camera, get 3, 4, 8 megabyte files out of it, but, so 1 megabyte JPEG file, not a big deal. Outguess is a technique that's been out there for quite some time. The source code is available online. And it's a little bit different in that it makes 2 passes on the JPEG image. On the first pass, it hides the message in the bits. And then on the second pass, it goes and changes unused bits to try to balance the statistics. And we're going to look at the statistics in the second half of the presentation. I'm going to make sure I get there. Okay? So the statistics of the file are better preserved with outguess, which makes detection more difficult. We have F5. F5 has probably been one of the toughest ones to crack. I think it came out in the early 2000s, 2002, 2003, somewhere like that. And it took about 5 years before researchers figured out a good way to detect stuff in F5. So it does things, it does a number of things. It's really sophisticated and it's really cool. So first of all, it hides in the bits, but it does not take the message bit and stuff it into the DCT coefficient. Rather, it looks at the least significant bit of the DCT coefficient and says, does that match my message? Of course, if it does, then you move on. If it doesn't, it subtracts 1 from that coefficient, from the magnitude. So 1 minus 1 is 0, and so it can't hide there. -1 minus 1 is really -2, but it subtracts 1 from the magnitude, so -1 goes to 0. So it can't hide in a -1 either. Okay? So one of the detractions is that you get more zeros with the F5 algorithm once you've hidden in the image. But as it turns out, it doesn't really matter. Other than that, it subtracts. So if you have a -2, then it subtracts and becomes -1. If you have a +2, it subtracts and becomes +1. And the reason it does that is trying to balance the statistics of the DCT coefficients. Okay, and we'll see that graphically a little bit later on, so I don't want to get into it too much right now. F5 is difficult to detect. Another thing it does is it inverts the meaning of a negative coefficient. So a 1 means a 0 on negative coefficients, and a 0 means a 1. That was also done to help keep the balance. It does permutative straddling, which is just a fancy way of saying it permutes the order of the coefficients that it hides in so that it spreads the message cryptographically throughout the entire image. It's not concentrated in one spot. And it uses matrix encoding. The idea with matrix encoding is we're going to use 3 DCT coefficients to hide 2 bits. So it's a little less efficient. You lose a little capacity from that, but By doing it this way, you only have to make a single bit change. No matter what your two message bits are, you only have to make a single change at most to one of the three coefficients. So it reduces the amount of actual change, because change in the coefficients is what gets detected. Change in the coefficients is what can be detected either statistically on the DCT values or on the other technique we're going to talk about, detecting the blockiness. Another technique, statistically invisible steganography, is what they titled it, but it can be detected. There is no technique that I know of that absolutely 100% cannot be detected. So what they do is they count how many non-zero DCT coefficients in a block. And if it's over a certain threshold, then they'll hide in that block. And if it's not, they won't. Now, the advantage of this is that they're actually kind of checking each block for if it's good, if it's suitable for hiding. So like say you have a smooth sky background or a sunset or something like that. That's less suitable for hiding than a complex background with lots of stuff going on in the image. And so they check that first, and if it's too smooth, they don't hide there. So only if it meets some complexity threshold do they hide. So in their threshold, they need between 20 and 39 of the coefficients to be non-zero. So it adds up, and then it adds up the coefficients, gets a sum, and then if the sum equals the message, we're good, don't change anything. If the sum doesn't equal the message, then you can add or subtract one from the largest magnitude coefficient. So they only make a small bit change for each block. Of course, you have a small capacity that way, but it is very difficult to detect. YAS, yet another steganographic scheme that resists blind Steganalysis, is another program that's out there. This one will select a larger than 8 by 8 block, like maybe a 10 by 10 block or 11 by 11 block, and from that select a sub 8 by 8 block. So in a 10 by 10 block, you can have 9 different 8 by 8 blocks out of that, and then it'll use that 8 by 8 block that it selects, which is different for every 10 by 10, and hide in that. Performs a conversion, the quantization, and then hides in those DCT coefficients. So that really is another way of kind of complicating extraction. Now, they ended up having some errors with that technique, and so they had to implement error correcting codes in order to compensate for that. My personal favorite is this one. This is the one that I use for the demo. This is the one where you saw the dog picture with the hidden data, with the hidden praying mantis and so forth. This high capacity DCT algorithm. It's basically an adaptive technique. Okay, this technique adapts to the DCT coefficient. So it hides more bits in the larger coefficients and fewer bits in the smaller coefficients. Of course, it can't use 0 or 1 for the same reason that we couldn't use 0 or 1 in the other situation. But with a larger coefficient, it can hide more information. I found to get the full effect of this technique, to get the best capacity, you have to use a quality of around 75. If you use less than that, then you've got to kind of manually lower the capacity. Otherwise, you're going to see a distortion. We'll see some examples of that too. So this one will choose the block to be embedded, and then it checks the block for uniformity, so it kind of does a little analysis on the block and says, is this a good block for hiding or not a good block for hiding? Even if it's not a good block, it still uses it, but it automatically scales the capacity that it tries to use for that particular block. So we have this alpha value, and we have the uniformity value, and it'll determine how many bits can I hide in that coefficient. And then it replaces the message bits, those bits with the message bits. So with one coefficient, it might only hide 1 bit, and it grabs that bit, puts it in there. For another coefficient, it might be able to hide 3 bits or 4 bits. So then it'll grab 4 bits of message and put that in there. More math, right? The idea with the uniformity is that if it's a uniform, as before, if it's a uniform block, we're going to be more sensitive to change than if it's a non-uniform block. So if it's non-uniform, we can hide more. That's the formula there, the sum of the squares. Take the square root of that. And there's a threshold. And if it's below the threshold, it's uniform. And if it's above the threshold, it's non-uniform. Lower frequency components can hide more bits generally. They're usually larger, but they cause more distortion. Okay, higher frequency components have more. You cannot hide as many bits in them because most of them go to 0. Remember, in the lower right-hand corner of the DCT coefficients, there was a lot of zeros. Those are the high frequency components. So we can hide any coefficient that's not 0 or 1. All right, so here's an example where we have our quantization table. There's 2 math calculations done. There's one calculation done based on this value in the quantization table, and one calculation done based on that value in the actual DCT coefficient. And it says how many bits can I hide based on the value in the quantization table, how many bits can I hide based on the actual DCT coefficient, and then it takes the smaller of the two. And the smaller of the two is what is the number of bits it can hide in there. Well, upon extraction, the extractor has to be able to determine, well, which blocks are uniform and which blocks are not. And if you're altering the coefficients upon extraction, that uniformity measure might be different. So the authors of this technique changed the quantization table in the lower right-hand corner, which is the highest frequency value, to a 1, and then use that as an indication, use that coefficient as an indication as to whether or not this block is uniform or non-uniform, which I don't like, because if you have a JPEG and there's a 1 in that value of the quantization table, that's a big red flag as to, hey, there's something going on here. There's never supposed to be a 1 in that high frequency coefficient quantization table value. So I did something different. I just modified the way the uniformity was calculated so that I didn't use any of the bits that could be changed. And then I don't have to modify the quantization table. So the program that I'm happy to distribute to y'all, if you want it, will not make any changes to the quantization table and will work just as well. All right, so here's an example. The program puts the parameters in the file name so that you can extract. Because when you extract, if you don't use default parameters, then you have to specify the actual parameters. This program is a very lab-oriented program, not a production program. Okay, it's designed for engineers and people that want to experiment and things like that, as opposed to a practical type application. So it doesn't self-detect, oh, this is the hiding technique, this is the alpha value, this is the U value, and so forth. So it just puts it in the file name so you can remember. So alpha was 8, U was 8, max bits was 5, and quality was 100. So we find about a capacity of about 25%, which is pretty large capacity to be able to hide in there. And it's very difficult to, well, there's a technique to detect it, which I'll show you shortly. Here's a quality of 80%. We still had 26% of the file size hidden. It's just a little bit smaller file size. And I don't know what happened to that image. That does not look like that. Did not look like that this morning when I went through my slides. So I'm not. There's a, I don't know. You know, that happened to me in class the other day too. I had like a big pink stripe across the bottom of one of the images in that. So I'm not sure what's going on with that one. That was with quality 60. Wow, these are not coming out at all. Okay, well, we'll have to come back to it. Here's one with quality 50. I don't know, can you, it's kind of tough to see up on the screen. I can see it on this monitor. Can you see the dots in the screen? Can you see the blockiness? I don't know. Yeah, I mean, you should be able to. I purposely chose this quality level to kind of illustrate that. In the top half of the image, you can see a lot of the blockiness up there, and you can see like black dots and stuff that's not really part of the regular image. It's much more apparent on a monitor than it is up on that screen. But if you hide cryptographically, okay, or if you use a password, then it spreads those dots all over the image. Okay, so you don't have it concentrated in the top half with nothing in the bottom half. It's spread all over the entire image. And of course, this quality level was chosen with the high parameters, high capacity parameters, in order to kind of illustrate that. All right, so how do we detect this stuff? Well, there's 3 levels of detection, okay, or 3 levels of failure, I should say, for steganography. 1 is detection, that's usually the big one. 2 is extraction. So some of the things don't complicate detection, they complicate extraction, okay, like cryptography, that makes extracting difficult. And the 3rd one is destruction. As it turns out, destruction is generally pretty easy for steganography. You can always just re-hide something else on top of whatever you hid before. When you look at the papers, the peer-reviewed professional papers, especially for this Steganalysis, they try to complicate the math. I don't know if they're trying to impress their professor or impress other people that are reading the paper. I mean, me, 2 + 2 is 4. Them, it's expressed as a summation sign. Okay? And that's just a simple example. I mean, average is expressed as a summation over the thing with equal probable events and all this. I don't know. I'm more of a practical type guy. Okay? Now, of course, with embedded data size matters for detection. You know, if you just hide a single bit, it's much harder to detect than if you hide to full capacity of the technique. So, general approach. As much information as possible is the key. Okay? What's your adversary's goal? What are they trying to hide? Okay, what are you looking for, in other words? What tools did they maybe use? What types of cover files are these? Are these in JPEGs? Are these in bitmaps? Are these in movie files? You know what? Okay. Check for tool signatures. Some tools actually leave a signature like that modified quantization table value. Okay, or maybe I found out early on that the code I used for the JPEG program always embedded a comment in the header. Okay, with the title of the book or whatever for the code. Well, that would be a big flag. You find JPEGs with that title, and you know that there's a steganographic program that uses that, then that's kind of a clear indication, right? So look for signatures. What's your adversary's goal? You know, what's your goal? Detection, extraction, or destruction? Okay, what tools did they use? What cover files? What types of messages? Text, encrypted, compressed, other images. Look for the signatures, as I mentioned that. Also specific types of distortion. The high capacity JPEG leaves a blockiness type of distortion when you use those lower qualities. That's a very common type of distortion in JPEG, is that blockiness. When you hide in bitmaps, you get like a fuzziness usually, but in JPEGs you get a blockiness. So 2 general approaches for JPEGs. One is to look at the DCT coefficients, and the program has that capability. I'll show you that. And then the other one is to actually check the blockiness of the image itself. And I'm talking about mathematically checking the blockiness, not, you know, a person checking the blockiness. Some of the techniques rely on training where you take, you know, 10,000 good images, run it through, get statistics, and then look for deviations from those statistics that don't make sense. The chi-squared test is a statistical type test, is used quite frequently to detect stuff in JPEGs. Basic histograms of the JPEG file do not work very well. Which one has the hidden data? Okay. A histogram, so you know, a histogram is a count of the different byte values. So over here is a count of 0, which is right there. Here's a count of 128. Here's a count of 255, and then everything in between. Okay, that's what a histogram is. So in a compressed JPEG file, doing a histogram of the file is pretty worthless. I mean, you can identify that it's a compressed file by the histogram. Like if you don't know even what the file is, if If you get a histogram, you can say, oh, it's a compressed file, but you can't tell anything about hidden data. However, in a natural JPEG file, the DCT coefficients are generally balanced. There's roughly the same proportion of positive ones as there are negative ones. Positive 2s, negative 2s, positive 3s, negative 3s, and so forth. And when we substitute, we didn't use 0 or 1, okay? And when we substitute into a positive 2, that changes to a 3. And we substitute into a positive 3, that changes to a 2. So we're swapping between 2 and 3 when we change the least significant bit. On the negative side, negative 1 becomes negative 2, and negative 2 becomes negative 1. So when we randomly hide in both positive and negative DCT coefficients, then we upset the balance of them. F5 does not upset the balance because it just subtracts. Okay, negative 1 goes to 0 and it's not used. Positive 1 goes to 0 and it's not used. Negative 2 goes to negative 1. Positive 2 goes to positive 1. So F5 maintains that balance. And of course, the swapping algorithm doesn't change any of the DCT coefficients at all. You'll get the same look of the DCT coefficients before you hide as you do after you hide. So looking at the DCT coefficient balance for the swapping algorithm doesn't do anything. That's when you have to look at the blockiness. So here's an image. We have size about 460K, quality 75. I lowered the alpha values a little bit on this one and used about 18% of the file size is available for hiding, and I used about 9% total. Only used about half the available hiding in this particular image. So here's a histogram of the DCT coefficients before. Okay. So the one in the middle is 0, and with 0, it's off the charts. I mean, it's so much higher that I didn't even use 0 to scale the coefficient. I mean, that's the point of JPEG, is to get a bunch of 0 coefficients. So there's like 5 million 0 coefficients, and the others are like 20 or 30,000 or something like that. Okay, and the program does produce this, and it also produces a textual file with the actual exact counts, so you can see. So the green there represents, on the left, -1. Gosh, I wish I had steady hands. And on the right, it represents a +1, okay? And then to the left of the green is what, red, that's the -2 count, and to the right, that's the +2 count, the red. So the colors kind of match up, so it's easy to see how we're comparing +1, -1, +2, -2, and so forth. And just looking at that, you can see it's fairly symmetrical. Well, there's the one with the hidden data. Now, that's clearly not symmetrical. It's very, very different, right? Now, as a human, that's pretty easy to look at and go, wow, that's really unbalanced. As a computer, it's actually a little bit more difficult, where you try to analyze the numbers and come up with a threshold that says, yeah, this is unbalanced and this is not. Because the numbers aren't exact. They're not exactly equal. But it can be done. This is after hiding with the LSB technique. What was the last one? The last one was after hiding with the high capacity technique. And then this one's after hiding with the LSB technique. Okay, it's still unbalanced. This one's after wiping. Okay, one of the features of the programs, because again, it's just an experimental type program, is that you can set all the message bits to 0. And I just call that wiping the message. Well, clearly with the DCT coefficients, if you wipe anything, it's really obvious. And then there's a random function also that just randomizes all the message bits with just a pseudo-random number generator. And it's still very unbalanced. Okay? Incidentally, when you randomize the message, that's a pretty good simulation of hiding an encrypted file. An encrypted file is going to look extremely random. And so the randomization feature here is a good simulation of hiding something that's encrypted. So when you're hiding, you can even tell, hey, maybe I'm hiding something encrypted versus something else based on the coefficient distribution. These are the actual numbers. I'll just point out that the 0 count is like 92% of the entire count. It's like 5 million compared to the others, so it's way out there. Of course, F5 makes that zero count higher, but it's still very high. So it's difficult to detect F5 by just saying, oh, there's too many zeros. Now, outguess, it used the excess capacity to readjust the coefficients to try to rebalance them. Okay? Swamp DCT, as I mentioned, doesn't change any coefficients. F5 subtracts, it doesn't substitute, so it keeps the balance. So we need another technique to detect JPEGs that use those types of hiding approaches. I tend to get ahead of myself. I don't like to read slides, so I know that all of you can read. So here's a technique for detecting F5. And this is just a very brief overview. If you want the details, there's a paper on it. Decompress the image and crop it by 4 columns. And now we get an estimate of the original image by that, okay? And all the hiding is lost. In fact, when you crop a JPEG, even by 1 column or 1 horizontal row, you're going to totally change the DCT coefficients. So if you're wondering, hey, does this have a message? And you don't really care what the message is, you just got to make sure that the message doesn't get through. Just crop it, and it'll be gone. Okay? So it'll crop that, it'll apply a blurring algorithm, and then it compares the predicted histogram with the stegohistogram, and it's able to actually calculate the message length, or the approximate message length from that. Here's the blockiness I was talking about. So this is just illustrating where we'll apply this formula, which also looks really ugly, but really all it's doing is getting the difference along that vertical column there, the difference along that vertical column, difference along that horizontal row, the difference along that horizontal row, and kind of measuring them. If you have a natural JPEG that doesn't have anything hidden, then those differences should be pretty small because it's going to look smooth. I mean, it looks good. You saw the pictures, and in the demo I've got a pretty high resolution image, and we'll look at that. So there shouldn't be much blockiness. Okay? But if you hide stuff, you get this blockiness. Even if we can't see the blockiness, you can detect a certain amount of blockiness with that. Okay, we got about 5 minutes. I think we're pretty close here. Okay. Again, extraction is more difficult because people will complicate extraction by using encryption techniques or by permuting the message. Knowing the method is critical. If you don't, if you're looking for swapped coefficients and it's hidden in the LSB or vice versa, it's tough to find the message. I talked about the sterilization already as far as randomizing the stuff or resizing the image or cropping the image. That's all very good for destroying the message. All right. So here's my command window. And let's see, what else do I need over there? Oh, the folder. So just to prove to you that this actually does work. Because anybody can stand up here and say anything, right, that it works. And I did script it out a little bit just to save time. So there's the command line. Now this command line is going to tell it to hide. The default algorithm is the high capacity. You can specify a couple of the other algorithms with the program. It's going to hide in this cat image, and it's going to hide a PowerPoint. Well, it's actually going to hide this presentation, but the presentation was too large, so I cut it down somewhat, so part of the presentation. Quality 100, alpha 8, U8, and then it's also going to collect statistics and create those DCT histograms. So we'll wait for it to finish there. This is a fairly large file, so it takes a few seconds on that. It's like 9 meg on the output. So here's the storage capacity. I don't know how well that shows up on the monitor. Oh, not too bad. About 1.8 megabytes. And then a bunch of other information. And here is, oh, sorry, it's on the wrong screen. There we go. There's the image with the hidden data. And we can really zoom in on this one. This was a high quality JPEG. That's me right there taking the picture. You see any distortion in that? And let's see, what was the statistics on that? Oh yeah, about 1.8 megabytes, so 18% of that file is my data, okay, not that data. All right, let's look at the histograms here. So here's the DCT before. Looks pretty balanced. Now this is a pretty large file, so the numbers are still not perfectly even, but in this graph, because the graph is very limited, they're so close, they're close enough that they look perfectly even in that. And then after. So there's a clear indication after that there's some altered data there, or that there's something unusual about that particular image. All right, so you still don't believe me because I haven't extracted the message yet. Well, here's the message. So this is not the extracted. This is what I actually put in there. And that's just, like I said, a truncated version of this presentation. Okay, so let's do the extraction. So for extraction, you just use the command word extract. And what did, oh, okay, hold on. Forgot to press Control-C. Try this again. There we go. And you have to give it the same alpha values and the same U value. You don't have to give it the quality, because the quality, all that does is adjust the quantization table, and the quantization table is built into the JPEG. So the Stego image, JPEG, has the quality in there, the quantization table in there. All right. So we'll set it off to work there. Oh, and then this is the hidden cat image right there. Hid cat. Okay, all done. And here's the extracted PowerPoint file. Well, I wish it would have appeared over here. Let's see. I'll try it again, because you're like, no, that's the one that you just showed, right? No, it's just appearing over here when I double click it. It doesn't want to come over there. Anyway, that is the one. Okay, so it's a truncated version of the presentation. All right. Anybody have any questions on that? I have a couple more demos. So this one is going to use a quality of 50%. And I'm going to hide in the dog. So there's a dog picture on here. Let's see, where is he? Right there. Okay. This is a much smaller file, so this will happen faster. And I'm just hiding this little text message in there, c2.text, so we can take a look at that. Where is it? There it is. All right, so that's what I'm hiding in there. Okay, all done. And here's the one, the hidden message. So this one was done at a quality of 50% with the high alpha value and the high uniformity value. And so you can clearly see there's something wrong with that image, right? But I did this one just to show you can still extract the message, okay? So if you don't care, you can still extract the message. So we'll do that, and it's very fast. And there's the extracted message. So same text message. Okay, one more real quick. This time we're going to do basically the same thing, except I'll use a password. And the password is black hat. And we have, let's see, where did it? Yeah, that's the hidden file with the password that we just created. Okay, and you see how it's spread out over the entire image from that. And then if you use the wrong password for extraction, like say we use the word black cat, Instead, entire message not extracted. The reason that happens is because I embed the length of the message in there, and then you see this is the extracted data, but it doesn't look anything like a text file. Okay, it's just all random garbage. But if you use the correct password, which was black hat, and then extract, then you got the right message. I will mention that in this implementation, I limited the effectiveness of the password to 56 bits. I didn't want to take any chances on violating ITAR regulations or something. I mean, I don't think it would, but just to be on the safe side, I don't want to go back home and get thrown in jail or anything. Anyway, that's it. That's what I have. Anybody have any questions? Yes? If you sample it up and then sample it back down, right? Is that going to destroy the message? Oh, no, you will not be able to recover the message at that point. That you will lose your data when you do that. Now, with steganography is very sensitive to change. A field called watermarking allows more changes. The goal of watermarking is to allow you to make manipulations like that and preserve the message, but the capacity is much, much smaller. There's one watermarking technique. You can rotate it, you can scale it, you can do all kinds of stuff, and the watermark is still there. They only hide 1 bit. Okay, so there's kind of this trade-off between capacity and robustness. Robustness being the more manipulation you can do. So there may exist some techniques that would allow you to do that, but it's going to be a much smaller capacity than you would have with JPEG. So with steganography, you're trying to maximize capacity, and so you have as much space as you can possibly get, but any little change will destroy it. Other questions? Oh, okay. Now, there's a lot of different pieces of software out there. This one will do, right now, it does the swapping, does the least significant bit, and it does the high capacity. There's one more technique I want to add, and I'd like to add an F5 type technique, but it's not in there yet. But yeah, there's a bunch of, there's other Stego programs, Easy Stego and JSteg, that hide in JPEGs as well. But there's no other one that implements the high capacity technique, to my knowledge. But yeah, there's no all-in-one. There's so many, there's hundreds. Well, I think another company documented about 1,300 or 1,400 different programs. Your question?
With the new JPEG standards being announced, do any of these techniques, are these techniques affected by the new lossless population?
I'm not sure exactly what standards you're talking about. There is a JPEG 2000 standard, okay, which came out around 2000 that nobody's using. That one actually uses the discrete wavelet transform. So you might be able to apply a similar concept, but I'm not really sure because I haven't worked with the wavelets that much. I'm not that knowledgeable on that. And then there is a lossless JPEG. There's no reason why you couldn't apply the concept to that either. Okay? Yes?
You mentioned extraction is extremely difficult. That's understood, but even conceptually, how would you do it?
Well, you try to figure out what tool they're using, you try to figure out what they're hiding, and then one thing you could do is say, well, let's just extract as if they used LSB, and let's look at the result. Let's extract if they used high capacity, the high capacity technique. Let's look at the result. Let's do the swap coefficients and look at the result. So you could do kind of a brute force type of thing to try to extract the data. But that's why knowing the technique is very important, because then you can narrow it down, okay? If you just have a file and say, here, there might be something hidden in there, you don't even know if there's a message in there or not, you got to do a lot of analysis. But if somebody says, well, here's a file, and we know they use this program to do it, that makes it a lot easier. So there's no silver bullet to extracting the data. If you're the forensic examiner, You try stuff, try to learn as much about what they're doing, what they're hiding as possible. Well, it kind of depends on computational power somewhat. If you can, if you're going to do a lot of this, then maybe you would write a program that would automatically do all these steps itself, produce all the results, and statistically analyze the results and see which ones look like what you're looking for. Like if they're hiding text, text has very set statistical characteristics. So then, does this result look like text? Does this result look like text? And you could automate that. So then it's just a matter of how fast your computer is. But the more you can narrow it down, the less time. But generally, it's a long process if you just have a file and see if there's something hidden in there. Yep.
You mentioned there were about 1,300, 1,400 programs that would imply a lot of demand. Do you have any thoughts about how much steganography is used and why?
I did do some research on that for the class, and actually it doesn't necessarily imply a lot of demand because it might just imply a lot of hobbyists, that like to write programs. I mean, not all of them are available, where you can just go download them. But the company that I'm referring to, they made it a business to try to collect as many as possible. But to get more to your point on that, I'm sorry, what was it? What was the question?
How much do you think steganography is actually used?
Oh, yeah. So I found there was about a half a dozen malware programs that use steganography. Zeus, Luron was one. Shady Rat was a very sophisticated piece of malware that was very targeted to actual corporate espionage, okay? And a couple others, I don't recall the name off the top of my head. I read in the paper one story about where they found a video of a terrorist had a video and they managed to discover that there was some hidden information in there, some hidden text documents and stuff. And then there was another instance a few years back where Russian spies were posting images to a website somewhere, or somebody was posting images, and then the spies would download the image, run the little Stego algorithm, and extract the data. And the way they found that, they didn't find it because they were looking at the images. They apparently captured one of the spies' computers, and then noticed on the computer that had this program. They say, oh, what's this? Oh, look, it hides data. Oh, look, it extracts data. Oh, look, they've been to these websites. Oh, look, these websites have pictures on them. So they had 90% of the knowledge already, and they just had to play with it. So I don't know how long it took to get to your point, but they had a whole bunch of information. We have the tool, we have the images that have hidden data in it, and so it's much more quicker to find something in that case than, oh, here's an image, see if you can find anything. Other questions? You're welcome to ask me questions afterwards. You're welcome to email me on the email address. The stego@satx.rr.com is the preferred address, but I'll respond on the other one as well. So thank you very much.